So this will be the video for the solution to questions 15 through 17 on the 116 exam 1 from winter 21. And so I'm collecting the questions together, sort of the three questions are linked to one single context. So this would sort of be typically representative of sort of the free response page for these, for these sort of one context and multiple questions on that context. The context is simple harmonic motion. This time I'm combining pendulum motion with the motion of a block on a spring, and so it's sort of linked somewhat to the tutorial on simple harmonic motion, but lots of the topics were of course addressed also in chapter 14, the first sort of 5 sections of chapter 14. So looking at the period of a block on a spring being a function of the mass of the block and the spring constant. The spring period of a simple pendulum only sort of being dependent on the length of the pendulum itself, and technically the period being proportional to the square root of that length. And the total energy is also some questions on the energy linked to at any particular time the potential energy plus the kinetic energy of the system. So this is sort of combined sort of lots of the topics and main concepts in the early sections of chapter 14. So the other two sections were basically damped oscillations of resonance, so that's 14.6 and 14.7. They're not included in this question or set of questions. So for question 15, let's start with the context here. So we have a pendulum that is hung directly above a block that's connected to an ideal spring. So I pull that straight from the tutorial, from the simple harmonic motion tutorial. Surface is frictionless and the block and the pendulum bob have the same mass, m. At time t1, the pendulum bob and the block are both instantaneous at rest. And we can see that the block here is at its negative amplitude, so it's sort of at rest, and the bob is at its leftmost position. So consider the following systems: the pendulum and the earth, block and the spring. For which of these systems can the total energy be determined without knowing the value of m? So if we think about, so I was trying to get into this idea, but it had asked a lot of questions in the practice exam where talking about that the energy of a block on a spring can be determined by just the initial conditions of the spring, the amplitude and the spring constant, and we don't need to know the mass of the block. So that's sort of the big idea. So the total energy is equal to U plus K. That's also equal to U max, which is equal to K max. Now in both scenarios, the K max is definitely dependent on M. So if we think for the spring example, so system 2, the one that isn't dependent on the M. So the system 2, we'll start with that one. U max is equal to 1/2 Ka squared. So not a function of the mass of the block. So it would be possible to determine the total energy of the block and spring system without knowing m. It's not if I know the spring constant, I know the amplitude. It is possible to determine the maximum energy in this spring block system. So that's the correct answer here. If I try to think about system 1 and why it's not correct, system 1. The potential energy is a function of the mass of the block. So U max will be equal to mgyi, where I define some initial point, but the initial potential energy, the potential energy is a function of the mass of the block. Oh, sorry, the mass of the bob. Sorry, excuse me. So that the potential energy is not, it's a quantity, it is determined dependent on m. And the kinetic energy, of course, is, for both scenarios, is also dependent on m. So only in the spring block system can we determine the total energy independent of the mass of the block. It's not true for the bob. The bob's different masses of the bob would have different maximum potentials, which would lead to different maximum kinetic energies. But I would need to know the mass of the bob in order to know the total energy of the pendulum earth system. But for the spring block system, all I need to know is the spring constant and the amplitude. Okay, so that was question 15. So this spring in the block. Question 16 is sort of linked, same context, but this is sort of linking to sort of the period. And for the oscillation and so on. So that's sort of the conceptual question that's happening here. Sorry, that was just an extra page in case I needed it. So this is question 16. So a short time later, we're told at T2, the block has reached its equilibrium position for the first time. So it's just gone from negative A to the equilibrium position. And the pendulum bob has reached its equilibrium position for the second time. So the pendulum bob has already gone through the equilibrium position, gone to its maximum on the right, and come back. It's coming back to the equilibrium position for the second time. And the yes, so then we're asked is, when the pendulum reaches its rightmost position for the second time, which of the following choices describes the position of the block? Okay, so what we can see here, so if we think of, let's see, so if we consider the delta t as t2 minus t1, we can see what happens. What's happened at this point is that the pendulum bob has gone through basically 3 amplitudes. So it's gone from its leftmost equilibrium to the max right, then max right back to the equilibrium. So it's finished 3/4 of its period. So this time is equivalent to 3/4 of t bob, because in a sense it's gone from negative A to to its middle, to its rightmost position, back to the middle. So it only has 1 more quarter to go to finish 1 full cycle. But the block has only gone from negative A to equilibrium, so that's only 1/4. So this is equivalent to 1/4 of t block. Okay, so then we can see that t block is equivalent to 3 t bob. Okay, so if we can sort of think somewhat conceptually. So for every quarter, so for every basically movement of 1 amplitude that the block makes, the pendulum bob goes through 3 of its amplitudes. So this is saying that when the pendulum bob has come back to the right for the second time, you got to think about what happens. How long will that take? Well, it has to go all the way to the left, so that's sort of 1 amplitude, then all the way back to the equilibrium, that's the second amplitude, then back to the right again, which is 3 amplitudes. So it'll again go through another 3/4. So that time, the time it takes to go back to its rightward position would be another 3/4 of its period. Because again, it's completing sort of 3 1/4 of its cycle. So at T2 is in the middle, equilibrium will take another quarter of the period to go to its leftmost again, another quarter down to the equilibrium, and another quarter to its rightmost. But so in 3/4 of the pendulum's motion, the block completes 1/4 of its period. So the block should be right smack over the bob again at being at x equals plus a, and be instantaneous at rest at that instant. So they'll again be in the same position, but at that point the block will have only completed half of its cycle, and the pendulum bob will have completed 1.5 cycles. So the correct answer here is that the block will be at x equals plus a and be instantaneous at rest. Okay, so no, that was a lot to go through. So I'll try to maybe just do a quick summary. So the key piece is recognizing that from that first information at T2, the pendulum bob has completed 3/4 of its period, and the block has only completed 1/4. And then for the time when the block gets back to the rightmost position, again, is another 3/4 from the equilibrium, which means the block just moves again just 1 amplitude to the right. So when the pendulum bob is when the pendulum bob is in the rightmost position for the second time, the block is right underneath it and instantaneous at rest, about to move to the left. Okay, so that's question 16, and I'll move on to question 17. Okay, so let's see here. So question 17 is the last question on the same context. The student wants to Alter the experiment such that the bob is always directly over the block as they oscillate. To determine that the decrease in the length of the pendulum, increase in the length of the pendulum by a factor x produces the desired result. So we can see that the pendulum's period is much shorter. So we want to basically, in order to increase the period of the pendulum to match that of the block, we'd have to increase the length. So we're saying we're going to increase the length by a factor x. So if we think again the equations, t is equal to 2 pi square root of m over k for the block, and t of the bob is equal to 2 pi square root of l over g. So if we wanted to increase the period of the bob such that it matches that of the block, we could increase l. Now, if the question is asking us if we want to do something else with let's suppose we want to change the block spring system such that its period is smaller to match the smaller period of the pendulum bob without any alteration. How would we decrease the period of the block spring system? Well, we could decrease the mass, but none of the options allow us to decrease the mass. So the option about the mass is we can increase the mass of the block by the same factor. So that would actually counteract our problem. That would make the period of the block even larger than it is. So it's sort of going in the wrong direction. Increasing the mass of the pendulum bob, the mass of the pendulum bob has no impact on the period of the pendulum. So it's only a factor of the length of the pendulum. So we can definitely rule out that the changing the mass of the pendulum bob is going to definitely do nothing. Increasing the mass of the block only would increase the disparity between the two periods. So we want to basically decrease the period of the block spring system. We can only do that. We can do that by decreasing the mass, not an option, or increasing the spring constant by the same factor. So the correct answer would be to increase the spring constant by the same factor, by which we change the factor of the length of the pendulum. So that would, in a sense, so if we didn't want to change the length of the pendulum, we wanted to alter the spring constant. Alter the spring block system, and the spring constant was an option. We could increase the spring constant by the same factor. Okay. Wrap up that question there, and then I'll follow up in a video for the full video for the tutorial questions.